In this video, we present the paper entitled Modeling a Three-Dimensional Chromatin Structure from IC Data with Transfer Learning. So first, we present the problem and partly what the IC data are and how they are used. So, as I said, the goal of this paper is to reconstruct the 3D dimensional structure of the genome with IC data, with biological data. Contrary to protein folding with AlphaFold, for example, we do not have any access to ground truth structures, meaning that there is no biological experiment that allows us, given a cell, to reconstruct, to visualize the ground truth structure of the genome within this cell. So instead, one uses IC data. To understand what IC data are, we deep dive into the IC experiment. So during the IC experiment, the genome of a cell is divided into n-equally sized bins, fragments, and the physical interaction between those fragments are detected and stored inside an n times n matrix for n bins, where each cell of the matrix tells you how frequent two fragments interact with each other. Intuitively, if two fragments interact very often, they are likely close by in space. However, the resulting matrix for a single cell is really noisy. So in practice, the IC experiment is performed over an entire population of cells. And so the resulting contact matrix, which is also called IC matrix, is the aggregation of contacts over the entire population. One can do this because the structures within the populations are very similar. So to summarize, the goal of this paper is to reconstruct the genome structure in 3D given the IC matrix, which is noisy and we don't have any ground truth data. So we work in an unsupervised setting, which makes, in terms of machine learning, the problem very hard. So we recover the original genome structure from a single noisy contact matrix. Now, here is our method for this paper. In this paper, we use machine learning to recover the structure. But because of the lack of ground truth, we employ a method which is called transfer learning to tackle this problem. Basically, we first train a network, an encoder network, which map a contact matrix to a ground truth structure. We first train this network on synthetic data, where we design the synthetic data such that later on, once we test the encoder on the true IC map contact matrix, it performs well in predicting the true genome structure. So basically, during training, we train on synthetic data where we have ground truth labels, and so we can produce a loss and so train the network. Then we test, and we finally test on the IC contact matrix and obtain the final genome structure. So the use of transfer learning allows us to work on synthetic data to overcome the lack of ground truth. And this is a really relevant idea. Now, what are the results of this promising method? To see this, we compute and output the structures of Tech3D, our network, compared to other state-of-the-art methods, Rich3D, GM, and MiniMDS. The structures are obtained from the dataset which is called the Trousseau dataset, which is a common synthetic dataset used in this field to compare the algorithm. And here's the ground truth structure. To compare structures with each other, we use the capture distance, which is a common metric to compare 3D structures in space. And here, we obtain that Tech3D performed the best in terms of capture distance compared to state-of-the-art algorithms, which shows actually that this technique of transfer learning applying for machine learning in this field is really promising, and we hope that it will pave the way for future deep learning solution for this problem. Thanks for watching.